Okay, so I guess I felt like there was some confusion when we left class today, and I realized after looking at this closer that although my approach was right, I didn't assign my priorities right on this question, number 3. So just to kind of clear some things up, I wanted to work questions 2 and 3 for you guys over again. So, and I'm going to do 4 and 5 as well because I think those are relevant for the exam. So on this one, if I'm looking at a molecule, so normally we are looking at molecules like this, right? If I'm looking at a molecule like this from this position, and I draw a Newman projection, I would draw whatever was dashed on the left and whatever was a wedge on the right, and the one pointing straight up in the plane of the page. That's how we get to Newman projections, right? So what we're doing here is going the opposite. So from our Newman projection, we can, if we are looking from this direction, we know that what's on the left is a dash and what's on the right is a wedge. So we can draw our Newman projection based on that. So I'm going to start with the front. Oh, that should be in the plane of the page, not a wedge. So I'm going to start with the front carbon. This carbon has a hydrogen coming straight up, a CH3 going into the plane of the page, a CH2OH coming out of the page, and then attached to it in an anti-position, so it's staggered, so these next will be pointing upwards. We have another carbon with a hydrogen going into the plane of the page, a CH2, CH3 coming out of the plane of the page, and then a CH3 down in the plane of the page. So this is the final structure that I get. But if you want to convert it into regular old bond line, 1, 2, 3, 4, 5, 6, that's how many carbons are. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbon 1 has an alcohol on it. Carbon 2 doesn't have anything. Carbon 3 has a methyl group, and it's attached to carbon 4, which also has a methyl group, and CH2, CH3 off of it. So you can kind of see from here. And then if you wanted to identify if these were Rns configuration, you could. But that's how you would go from Newman projection to the bond line. And then to name it, that would be hexane. There's a 1-OL. There's a 4-methyl and a 3-methyl. So that total would be... let's see, I'm running out of room. 3, 4 dimethyl hexane 1-ol would be the total name. And technically, you would need to assign R 3R, 4R, whatever it is here. That's not necessarily right. I'm just putting that there. But in this case, I think that this question tests the concept enough, so you don't need to worry about assigning those. If you want to, you can, but it's not a priority. Okay, so from the next one, and those are just me showing you what you would need to do to draw it. Draw the most stable form of this cyclohexane. So this is 1OH, 2 isopropyl, and 3 ethyl. Okay, so I'm going to determine if each one of these in the R and S configuration is a wedge or a dash, and then I'll convert that to a chair conformation because the most stable form is going to be a chair conformation. So if this were a wedge, you'd have a hydrogen pointing straight back, so that kind of makes it easy. So this is 1, and then you have 2 carbons. And between these 2 carbons, we'll call them carbon A and carbon B. Carbon A is attached to a carbon and 2 hydrogens. Carbon B is attached to a carbon. Carbon B is attached to a carbon and a carbon and a hydrogen. So between these two, carbon B is the higher priority and carbon A is the lower priority. So if we connect these, 1, 2, 3, that's R. So that's a wedge. Okay, so now let's draw this whole structure over again and try to tell for the one on carbon 2. Okay, so this carbon is actually attached to 3 carbons, carbon A, carbon B, and carbon C. So carbon A is bonded to an oxygen, a carbon, and a hydrogen. Carbon B is bonded to 2 carbons and a hydrogen. And carbon C is bonded to 2 carbons and a hydrogen. So carbon A is the highest priority. Now between B, we'll go to the next point. And actually both of them have, B and C both have one methyl group attached to them. So if you compare these two, this carbon has CH, so has a carbon and 2 hydrogens, and this has this has 3 hydrogens only on that carbon. If you go from B out 1, either of these have that. Where both from carbon C, both of these actually have a two C's and a hydrogen. So between these two, actually, C is going to be the next highest priority and then B. So that is S, and that's what we want. We want an S configuration. So we're also assuming that this is a wedge and the implied hydrogen is a dash. So now let's go to the last one. Okay, so we're looking here. So this is also bonded to 3 carbons. We'll say carbon A, carbon B, and carbon C. Carbon A is bonded to a carbon and 2 hydrogens. Carbon B is bonded to a carbon and 2 hydrogens. And carbon C is bonded to 2 carbons and a hydrogen. So carbon C is the highest priority. Now we're just comparing A and B. So both of these had a carbon and 2 hydrogens. If you go one further, A has 2 carbons and has 1 carbon and 2 hydrogens, and B has 3 hydrogens. So 2, 3. So this is also S. So all 3 of these should be wedges. So if all 3 of these are wedges, hang on, let me grab an extra blank sheet of paper because I'm running out of space. So if all 3 of these are wedges, then they're going to alternate. Axial, equatorial, axial, equatorial. So it can be equatorial, axial, equatorial, or axial, equatorial, axial. I'm going to pick equatorial, axial, equatorial because then they would be the most stable conformation. So we'll have OH in the equatorial, we'll have our isopropyl in the axial, and then we'll have the ethyl group in the equatorial. So I hope that clears that one up for you guys. I know that's kind of confusing, but I think that should hopefully help. And then for question 4, draw the dash wedge structures is very similar. Draw the dash wedge structures for all stereoisomers of 1 bromo 3 isopropyl. So this is not the most stable. This is dash wedge. 1, 2, 3. So 1 bromo, 3 isopropyl. So this is one option. The next is, well, I guess I could do the mirror image of this, and next would be bromo being a dash and the isopropyl being a dash. And then we'll have a diastereomer of this one where we have, this is the same, but this is the mirror image. And then we'll have a diastereomer, the mirror image of this, which is another diastereomer to the first one, which would be bromo. And there you go. And I know sometimes it can be tempting to think like, wait, if these are both dashes, can't you just flip it over and they'll both be wedges? But if you do that, then this side would actually be the isopropyl, right? This is the isopropyl. If you flip the isopropyl over, that would be on top. So this becomes the bromo. So if they're both wedges this way, then it's the mirror image, right? This would be the isopropyl, and this would be the bromo. It'd be the mirror image reflecting across that way. So either one of those is appropriate to draw, if that makes sense to you. This personally just makes the most sense to me. Okay, and then we need to identify if they're R or S. So we'll do that the same way. With this being a wedge, this would be 1. And then between these two, these are the same. They're both carbons. They're both bonded to 2 hydrogens. Then we go to the next one. Well, this carbon is bonded to 2 hydrogens, but this carbon is bonded to another carbon. So this is 2 and 3. 1, 2, 3, that's our configuration. So this is also our configuration. So then we'll look at this one. So this is bonded to actually 1, 2, 3 carbons. So then we have to go to the next one. This carbon, so we'll say carbon A, B, and C. So carbon A is bonded to 2 hydrogens. Carbon B is bonded to 2 hydrogens and a carbon, sorry. Carbon B is bonded to 2 hydrogens and a carbon. And carbon C is bonded to, that's right here, is bonded to 2 carbons and a hydrogen. So this is actually the highest priority. And then between these two, well, these are exactly the same. A and B are the same. So now we need to go to D and E. Between D and E, D is bonded to 2 hydrogens and a carbon, whereas E is bonded to a bromine, a carbon, and a hydrogen. So that bromine outranks the carbon. So then this would be the second priority, and this would be the third. So this is S configuration. So this one is RS. If this is S, then the inversion must be R, so that's RR. So let's see, this would be R. Oh, this is inverted, so this would be SR, and this would be SS. Okay, and then for question 5, Fisher projections for all stereoisomers of 2,4-dimethylhexanol. So let's draw hexane. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and 3 has the OH. Okay. So I'm going to identify the chiral centers that need to be included in the Fisher projection. There's one right here. This might seem like a chiral center at first, but it has 2 methyl groups. So 4 different things are not attached there. So just these 2 are chiral centers. So those will be the focus of my Fisher projection. And it doesn't matter the chirality now. I can put the OH and this hydrogen that's implied on either side. It doesn't matter because I'm going to draw all the stereoisomers. And then here I'm going to have my methyl group on one side, and it doesn't matter which side it's on. And then I'll just write CH2, CH3 down here, and up here I'll have CH, CH3 too. Okay. So if I want the enantiomer of this, I will just go ahead and draw the mirror image. So that's HH, OH, CH3, CH2, CH3, and CH, CH3 too. So that's the mirror image. And if I want a diastereomer of this, I'll only flip one of them. CH, CH3 2, OH, H. And then I'll do, so that's the mirror image of the top one. Oh no, that's the same of the top one, and I'll do the mirror image of the bottom one. So H, CH3, CH2, CH3, and then the mirror image of this should be the last diastereomer. Let's see, so H, OH, CH3, H, and CH2, CH3. Okay, and now I'm going to assign Rns configuration. So this would be highest priority, and then between these, let's see, this carbon is bonded to 2 carbons. This carbon is bonded to 2 carbons. If you go to the next one, the CH3 is the same, but this has a longer chain. So this would be 2, and that would be 3. So 1, 2, 3. So that's S, but the hydrogen's coming towards us, so that's actually our configuration. And then down here, let's see, we'll do the same thing. So this is 4, obviously. So it's bonded to 3 carbons. This carbon is bonded to an oxygen, a carbon, and a hydrogen. This carbon is bonded to a carbon and 2 hydrogens, and this is bonded to 3, so this would be 1, 2, 3. So that would be R, but the hydrogen's pointing towards us, so it would be S. So this is RS. So the mirror image of this would be SR. If this one's the same, it's still R, but this bottom one would be R, and this should be SS. Oh, sorry, I didn't realize off page. So hopefully that's helpful for you as far as the group work goes. I honestly think that'll clear up a lot, and I hope it's helpful to you.